Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called shortest path in binary matrix. So we have been given one n by n square grid. Each cell is either empty or blocked. Empty means it is 0 or it is 1. 1 means it's blocked. So what we need to do? We need to find a clear path from top left to bottom right. Okay. So these are all the conditions have been given. So one condition is like basically this would be we can move it directionally, right? It directionally means including diagonal as well. And C1 is at location, so we need to start from 0 0 and we need to end at n minus 1 n minus 1. Okay, and Ci is located at R and C. Okay, so R and C is like this is just coordinates. Okay, and we need to return the shortest length clear path from top left to bottom right. If such a path does not exist, then we need to return -1. All right, very good. So these are the in the note section. The length can be like from 1 to 100, and RC is either 0 or 1. So it is in fact a binary matrix itself. Either it will have 0 or 1. So what I did, I copied this diagram here as usual, just to understand this problem little bit here. So we will start from the 0 0 coordinate. So we will start from here and then we have to go here, right? So what will be the shortest path in this case? 2. Why it will be 2? Because we cannot go this way because it is 1, right? So in the problem itself they mentioned like blocked cell is the 1, so we cannot move to the 1. Also we cannot go to this direction and then this because we cannot move to 1. So we can start only from 0 to 0. So start should be at the 0 and end should also be at the 0. All right, now the second example. So we need to start from 0. So this is 0 0 coordinate. We will start from here, 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 here. So what is the length here? 1 1 2 3 4 5. So 5 is one option. What is another shortest length can be? We can move like this as well. Remember, we can move diagonally as well, right, in this problem. So it will be like 1 2 3 4. So another answer will be 4 and we need to return 4, not 5, because 4 is the shorter or the minimum than 5, right? So we need to find the shortest path. Also just remember we cannot go to the blocked cell because we cannot move to the cell that has the value 1. So 1 means here the empty cell, not the empty but the blocked cell. 0 means empty and we can move only to the empty cell. Alright, so this is the problem. Now how we are going to solve this problem? Let's come to that part as well, right? So here what we are doing, this is the matrix itself, but we are starting from one point, and from one point we are moving eight directionally, right? So here what eight directionally mean, right? So if we see the direction here, right, so this middle point is 0 0, right? So this is 0 0, right, in the middle. And if we see here, this is 1 comma 0, right? So if I use the better typing, maybe I can use this guy. Okay, so this is 0 comma 0. Okay, and here coordinate is basically 1 comma 0. Here coordinate is basically 0 comma 1. This coordinate is basically -1 comma 0. This coordinate is basically 0 -1. So how did I calculate these coordinates? I calculated like this x-axis, right? So x-axis is 1, so that's why I'm saying 1, and y-axis is 0, right? So I'm here, and if I move like 1 unit of the distance, then it will be 1 comma 0. If I am here, that is at the 0 0, and if I move like y-axis 1 unit of the 1 unit of the distance, then it will be 0 comma 1. Similarly, if I move x-axis to the 1 unit, then it will be -1 because it is in the opposite direction. Similarly, if I move the y to the downside direction, then it will be -1 at the y coordinate. Okay, so that's how we see like which direction we are moving. Now we can move here not only 4 direction, but we can move to move to 8 direction as well, right? So 8 direction means we can go diagonally as well. So we can move this direction, we can move this direction, we can move this direction, we can move this direction as well. Okay, so what does that mean? That mean is basically, so what will be this direction, right? So if we will see from here, basically this x-axis we are covering, so this will be like 1, right? And y-axis we are covering at this, so this will be 1 comma 1. Okay, so what will be this axis then? This will be 1 comma 1 here, and the opposite direction, opposite diagonally, what it will be there? -1 comma -1. How it become -1 comma -1? So -1 we are taking this x-axis, and -1 we are taking this y-axis, right? Because it is in the middle, right? So we are not covering the 0, so it's not on the 0, it's not on the 0 direction, right? It's not covering the 0 coordinate, it's covering in the middle, so that's why this is diagonally, right? I hope this is clear, right? So -1 we are taking this x-axis, and -1 we are taking this y-axis, that's why it is -1 -1. Now what about this coordinate, right? So this coordinate will be -1 comma 1, right? So what we did here, -1 is this x-axis, and y is this x-axis, sorry, y is this y-axis, and that is 1, and x-axis is -1, this one. Now similarly here, what will be the coordinates here? This will be basically, we will see from here, so this will be x-axis and the y-axis, right? So in fact this will be 1 comma -1. Okay, so we took basically 1 from here, this is x-axis, and then we took y-axis from here. And the intuition to take from these x-axis y-axis is basically, because we are covering here the x distance, right, 1 distance, and we are covering -1 distance on the y side, that's why we are taking. And another minor observation here is, here it is 1 1, then the opposite will be -1 -1, and if it is -1 1 here, and then opposite will be 1 -1, so they are just opposite in the sign as well. So if one is positive, then another will be negative here, right? If they both are positive, then both will be negative here, right? Similarly here as well, if it is 1 0, and this will be -1 0. So why we need to understand this coordinates? Because we will be using these coordinates in our code, right? So we will start from 0, starting from 0 coordinate, 0 0 coordinate, and then if we have to go left, right, not left, but if you have to go right, then we will increase our x coordinate. If we have to go left, then we will decrease our x coordinate, right? So we will do -1. If we have to go up, then we will increase y coordinate. If we have to go down, we will decrease the y coordinate. We have to go diagonally, then we will decrease x and y coordinate. If we have to do diagonally up, then we will increase x and y coordinate. Similarly, if we have to go diagonally this side, like left side, right, then we will decrease x coordinate and increase y coordinate. Similarly, if we have to move basically diagonally downside, right, then we are increasing by x coordinate, and we are decreasing y coordinate. So this is like important thing, and then to know that what are 8 direction here. Okay, all right, so now let's quickly move on. Okay, so here the pattern direction we have understood the problem itself, what is the problem itself. Now what is the pattern, right? So here the pattern is basically, we are starting from one node. If we consider this matrix as a graph, and we consider these cells as a node, graph node, then we can say, like, if we are starting from one particular node and we are moving it directionally, and we are checking, okay, is there any one, is there any 0 or not, right? Not 1, because 1 is the blocked cell, right? So 0 is the empty cell, we need to move 0, not 1. So we are checking if there is any 0 or not. There is not any neighbor, that is 0, right? If we move only two direction, horizontal and vertical, but if we go diagonally, then 0 is still there. Then we will move to this direction, and then we will find the 0, and then we will record the distance as well. How we are going to do that? Let's go ahead and do that. So this strategy is called the breadth first search, right? Breadth first search, we pick one node and we traverse all the neighbors, right? Once we find the neighbors, we store them in the queue, and then we again pick another neighbor, and then we traverse all the eligible neighbors. So that strategy is called the BFS, breadth first search. Okay, so in the breadth first search, what we do, we start with the queue, right? In fact, this will be smaller queue, because this is very less elements in the matrix. And let's say, if we say like 0 1 2 3, the location of this matrix is 0 1 2 3, or I can create another parallel matrix here. So 0 0 1 2 3. This is just the locations, right? So what we will do, we will check this 0th location, and 0th location is this, and then we will store that into the queue, right? And that is 0. Then what we will do, we will pull this from the queue, right? And once we will insert into the queue, we need to mark it as a visited as well. Okay, so we will mark this guy as a visited as well, and then we will pull from the queue, and then it will check the neighbor. What are my neighbors? So neighbors are like 1, this is at the 1 location, and this is at the 2nd location, right? So they both are 1. Now it will go diagonally and it will check 0. Okay, so it found another 0, and this 0 at the 3rd location, so we will store 3 into the queue, right? And then we will poll this 3 as well, and at every level we are incrementing distance as well. So this is level 0, right? So if initially level is 0, right, then we increment this 0 plus 1 1, and this is the 2nd level, so we increase this level as a 2, and then we find, okay, this is my 3rd location, what are my neighbors? So this is another neighbor upside, and this is left side is another neighbor, but they both are 1, right? So they are not eligible to be neighbors, right? The only eligible neighbors are 0. So if they are 1, then we don't find any neighbor. And also we will check these coordinates, right? So if this is 3, means this is the end of the matrix, right? So total size is basically, this is 2 by 2 matrix, right? So 2 by 2 means they should be basically uh, 2 cross 2, right? So we find these values on the coordinates. In fact, I am using just the random sequence number, so that's why it's not matching, but in actual they will be like something like this, right? 0 1 and then 0 1, right? Something like this. So basically 2 by 2 matrix, if it is there, if it is the last cell in the matrix, then we are going ahead and returning our distance, that is 2. So that's what we need to do. Okay, the sequential number I'm taking just to understand the concept. Let's not mix these sequential number with the code. We are not going to use these numbers in the code. We are going to use we are going to store the coordinates, actual coordinates. So these coordinates we are going to store in the code itself, right? 0 1 1 0 or something like that. Okay, now let's move this example, okay, so that picture will be a little bit more clear, and then we will quickly jump to the code. So let's try to understand this guy. So this is our matrix, right? And this is our queue. Okay, so this is queue, this is another matrix again, just for 1 2 3 4 5 6 7 8 9. I'm just taking these sequential numbers just to represent the locations of each cell, so that it will be easier for us to point out. So this is 1st location, this is 2nd location, this is 3rd location, this is 4th location, this is 5th location, this is 6th location, 7th, 8th, 9th. Okay, this is 9th location. So that's the mapping of the locations to understand the concept. All right, so we started from the 0 0 cell, right? 0 0 coordinate, x is 0 and y is 0, but in fact here the location we are assuming that it's 1. So we will be going ahead and insert 1 here. So anyways, this is I was taking like 0 and 1 format, and here I'm taking 1 2 3 4. So just try to understand the concept. Let's not get confused between whether it starts from 0, it starts from 1. It really does not matter. What matters is whether we are able to understand the concept or not, right? So we uh, inserted this cell, this location here to the queue, and that is 1, right? What we will do now, so our label will be initially 0, right? And then once we insert here and we mark this as a visited, then label we will make it as 1, right? Because queue size is 1 at this point. Now we polled 1, right, and it will check the neighbors, right? So what is my right side, what is my downside? So downside is 1, and right side we found another 0, right? We found another 0, and that location is 2, right? So what we will do, we will insert this to the queue, that is 2. Okay, and then We already covered this part. And then we will poll this guy from the queue. Okay, because queue size is now 1 only, so we poll this, and then label will be 2 at this level because this is second level. Now we will check and we mark this as a visited. We will check, okay, right side it is also 0 and downside it's 1, so this guy is not eligible, right? So this guy is not eligible. Only eligible is this 0 guy, because we have to ignore 1, we have to take only 0. So now we came to here and that location is 3 here, so we will insert 3 to the queue and we will mark this as a visited here. Okay, now there is another eligible node here, because remember we can move diagonally as well, right? We only not need to move only 4 direction, but we need to move diagonally as well. So it will go diagonal. Okay, and that location is 6 here, right? And that is also 0, so we will insert that also into the queue, right? So from this level means label this cell, cell number 2, there are we visited 2 cells, and that is 3 and 6. So now queue size has becomes 2, right? So now the queue contains 2 elements, 3 and 6, and that is the location 3 location and 6 location. All right, so now this is the level 3. We incremented the level 3 here. Okay, and it's having 3 and 6. So now we will poll 3. What is at the level 3? So 3 is basically this thing, so we will poll this guy 3. And from the 3 we will check, okay, what is my left side? That's already visited, right? And downside, that's also already visited, because we inserted to the queue and we already marked it visited, so it will not impact anything. Now what about 6? So once we will poll 6, so 6 is this guy, and it will check left side, this is 1, so this is not eligible, right? It cannot go outside of the matrix, so it cannot go right side. It will check the downside, and that is 0, right? And what is this location? That is 9. We will go ahead and insert 9, right, to our queue, and we'll mark it as a visited as well. And then we will check, okay, if this neighbor, if it is having any eligible neighbor or not. So it does not have, right? Because this left side is 1, and it cannot go outside of the matrix. It cannot go down because it cannot go outside of the matrix as well. So we will poll this, mark it as a visited, and we will check, okay, we already reached to the end of the matrix, right? So this is, we will start from the top bottom and we will end to the this bottom, right? We will start from the uh, not the bottom, we will start from the top left and we will end to the right bottom, right? So we will start from the top left and we will end to the bottom right, basically. So this is end of the matrix anyways. Okay, so once we found this end of the matrix, and here also the queue size was 1, so we increased our label, and then this will be our output. Label is our output. So I hope the picture should be clear at this point, at the high level at least. And once we will create couple of placeholders, I think it will be more clear. So let's go ahead and do that. So let's say if grid is null and grid dot length equals to 0, what does that mean? If matrix itself is null, then we have to return -1. Why? Because the problem is saying if there is no path, if such a path does not exist, return -1. So we are going ahead and returning -1. All right, now let's take the m and n. So m is basically grid length here, and n is basically column length of the matrix, right? So okay, now what we will do, we will take the queue, because it is the BFS, we are following here the BFS strategy. So new linked list. All right, queue dot offer. What we will do, we will store our 0 0 coordinates here, because we are starting from the top left, right? So we are starting from the top left here, so that's why we are storing 0 0 coordinates here. Our location is 1, but in the code we are storing 0 0 coordinates, these coordinates. Okay, and now we can take the visited as well. So boolean visited array, new boolean mn, and visited 0 0 is true. Okay, And now we can apply our BFS template here. What is BFS template? So we will check the queue. If queue is not empty, then we will take the size of the queue. What is the queue size here? So queue dot size, and then we will go ahead and iterate that many times. Size I plus plus. So here if we see our diagram, right? So initially the queue size is 1, we iterated only one time, we increased our level. Queue size is 1, then we iterated only one time. Here the queue size is 2, so we iterated 2 times, 3 and 6. And then the label is basically for these two elements, and we increase the label as a 3. Okay, so whatever the queue size is there, that many number we need to iterate. So what we will do here, int current queue dot poll. Why it is one dimensional matrix? Because we are storing coordinates x and y, so it is one dimensional matrix already we are storing here. One dimensional means these are the coordinates, right? So we are storing these coordinates in the pair 0 0 0 1 0 1, like whatever we will be polling from the queue. So that's what it is, right? So current x is first 0th item, current y is second item in the first index in this metric, in this one dimensional array, right? So 0 is the x coordinate and y coordinate. Similarly here, x coordinate, y coordinate, x coordinate, y coordinate, x coordinate, y coordinate. Okay, all right. So let's come to here, and now these coordinates we need to move 8 directionally. Okay, so here let's take the 8 direction here. So 8 directions are these coordinates, right? All these 8 coordinates, right? So let's go ahead and take these here. So these are 0 1 1 0 minus 1 0 0 minus 1, and then 1 1 1 minus 1 minus 1 1 and minus 1 minus 1. Okay, so we took all these 8 coordinates, 8 directions, int x equals to current x plus direction here 0, int by equals to current by plus direction 1. Okay, now let's go ahead and check the base condition as well. So x is less than 0 or x is greater than m minus 1, or y is less than 0 or y is greater than n minus 1, or if they are visited. Okay, so x by is visited means it is true, right? So let's say we are starting from here, right? We are starting from here and we inserted this guy already to the queue, and we mark this as a visited. Similarly, we will come here, and if it is 0, then we mark it as a visited, and if it is already visited, then we are going ahead and we are ignoring that, right? It should be either it is visited already, or if it is 1, right? 1 means not 0, so we can check that condition as well. So either it is visited here or it is not 0, right? It means if it is 1, right? So these are the opposite conditions. If these conditions meet, then we are continuing, means we will not be executing any code here after continue, right? So it will check for the next direction. Okay, so what I can try to little bit format this one for better readability, but here, okay, so now it looks better. So continue, and now grid x by, right? So what we can do, we can now, if it is not outside of the boundary, and if it is not visited, and also if it is basically not 1, right? If it is 0, then we are going to insert those coordinates to the queue. So x comma y, and then we can mark those coordinates as a visited, right? So x y is true. So what are these coordinates? These coordinates are 1, sorry, these coordinates are the cells that contains 0, not the 1, right? So if it is 1, then we are continuing, right? So if it is 1, then we are skipping those, but if it is 0, then we are inserting to the queue and we are marking it them as a visited, whatever we have understood here. Okay, and that's pretty much it, right? We need to take another variable here that's called label, right? Let's initially it is 0, and after processing queue, right, once we process the queue, right, so for example here the queue size is 1, then we are incrementing at label 1, and queue size is 1, then here also we are incrementing label another, incrementing the label, and if it is queue size is 2, we are processing these two elements, and then we are incrementing the label, right? So this label we need to increment outside of this size, right? So either we can increment here or after that, but basically we need to increment this outside of the for loop, outside of the size, because we are processing these neighbors at one shot. Like these neighbors can be 2, 3, or n number of the n number of the items, right? We have to process in the queue dot size that for loop, right? And then we need to increment this label. All right. So once we increment this, and then we need to check if it reached here to the end or not. So if current x equals to m minus 1 and current y equals to n minus 1, then go ahead and return label, right? Otherwise what we are going to do here, we are going to return -1. So for somehow it did not reach to the end coordinates in this PFS traversal, then we are going ahead and return -1 in the end. So that's one thing. Okay, now let's quickly check to compile if it is getting compiled or not. So looks like this code is getting compiled. Now let's check the second example as well. Okay, and here we need to cover another edge case that I will show here. So this is also getting compiled and it's working fine. Okay, so edge case, what I was talking about, let's say for example we are given some metrics like this. Okay, so let's say we are having this matrix and we are starting with 1 and 0 0 0 0 0 0 0 and then 1. So what about this test case, right? So we need to start from 0 0, but it is 1, we cannot move to the 1, right? And also, so this should return, this test case should return -1. So we need to handle this scenario in our code, right? Similarly, if there's another test case here, it started from 0 0 0 0 0 0 and then 1. So it started from here 0, and then very good, it come here, come, and then it wants to, because it's the minimum distance, right? So it will diagonally will be the minimum distance rather than going vertically or horizontally, obviously. And then then diagonally, if it will come here and then find 1. Oh, so 1 means like it's blocked, so it cannot go. So we need to handle this case as well, right? So if the top left is 0 or bottom right is 1, so top left is 1, not 0, right? So 0 is the we can move, right? But if it is 1, we cannot move. So if top left is 1 or bottom right is 1, then it is the invalid case, we need to return -1. So let's go ahead and handle that case as well in our code. What does that mean? How we will handle? We will check here. So grid 0 0, if it is 1, or grid m minus 1 n minus 1. So let's move this part to the above to this m minus 1 n minus 1. If it is 1, then we will return -1. Okay, so this is to handle the edge case as well. Now let's try to submit and let's see if it is the test cases are getting passed. So looks like this concept is working fine. Now another optimization what we can do, we can get rid of this visited boolean additional matrix. How we can get rid of this? Because observe here we are having only binary matrix, right? It is only 0 1. So what we can do, we can exploit that property, right? We can use that property 0 and 1 property. So for example, if I remove that one and if I remove this check, then what I can do, I can check like if it is 1, then skip that, and then basically rather than visited true, I can do grade x by equals to 1. So because I know if it is coming after continue, then it means that this grid cell is 0, right? If it is coming here, right? So if it is coming here, it means the cell contains 0, right? So if cell contains 0, I can update the cell value as 1, right? So then I can get rid of the visited boolean array, and then I can directly use this property, and if next time if it check 1, it means it is already visited, right? So that's another optimization that we can have. Let's quickly check to compile this one if it is working fine. Let's see if it is also working fine. So see very slightly improvement in the runtime as well, right? So not too much drastic, but it at least little bit optimization. Time complexity wise, it will be m into n. Space complexity wise also into m into n, because we are visiting, in the worst case we have to visit all the cells of the matrix, right? So that's why we are saying like m is the rows count and n is the columns count, then it will be m into n. And space complexity also we are maintaining here the queue, so in the worst case we have to uh, basically store all the matrix itself into the queue. Basically we are just going through and we are storing the coordinates, but in the worst case we have to go through each and every cell to the matrix. So this will be m into n. Okay, so quickly before ending this video, this is like the binary matrix here. The only different from the normal pattern that it is only 8 directional, right? So we can understand the 8 direction from this diagram. What are 8 direction looks like? Also we have to start from 0 0 coordinate and we have to go to the bottom. Another important observation is we can only visit 0. So if it is not 0, means we have to handle this case like if starting is itself is 0, or the bottom right is also not 0, right? So top left is not 0 and bottom right is not 0, then we cannot that is the invalid case. So we are handling this case as well here, right? So this edge case we need to handle, right? Otherwise it will be failing for those cases. So if it is 1, then we are straightforward return -1. If it is grid is null, then also it's not valid, we cannot um, uh, fulfill this criteria, right? Sorted path we cannot found. But if we take like these 8 directions in this 2-dimensional array, and then we apply our breadth first search pattern here, then we can just traverse all the eligible neighbors that contains 0, and then we can at every, after processing each and every element in the queue, we can increment the label size, right? So every level we will keep incrementing the label, and in the end, once during in the end basically if we don't find anything, then we are returning -1. But if we in the but during the BFS traversal, if we find the coordinates, if it reaches to the end, then we are returning the label, whatever the label we are. So let's say for example at this label we are 4 because we reached to this end of the matrix. So hopefully this might be little bit useful. Thanks a lot, have a good one, bye.